what about this function? X is continuous, the constant 2 is continuous, the sum of two continuous functions is continuous, so the top is continuous, the bottom is continuous, but when we divide two continuous functions, it'll be continuous except where the denominator is equal to 0. So this is continuous except where cosine x equals 0. Let's see, cosine x equals 0 when x equals pi halves plus any multiple of pi. So say n here is an integer, maybe n an integer in this case. So this is continuous everywhere except at pi halves plus multiples of pi. Any polynomial has to be continuous because powers of x are continuous, and constants times powers of x would have to be continuous because they would be products of continuous functions, and then sums of continuous functions are continuous. So the top is definitely continuous because it's a polynomial. The bottom is definitely continuous because it's a polynomial. Our only question might be, is the denominator ever 0? So, well, let's factor this and see if we can find places where the denominator might be 0. Looks like if I can factor using a 2 and a 5, if I use a negative 5 and a plus 2. Okay, so this is continuous everywhere except at x equals negative 2 and x equals 5 because the denominator is 0 in those places. Let's see, what about this? This is pretty good. If it was just plain sine x, we could be in trouble because sine x is occasionally negative 1, and so we could get 1 minus 1 would give us 0 in the denominator. But since it's sine squared, sine x is continuous, so sine x times sine x is the product of two continuous functions, so that's continuous. So we have continuous plus continuous, and sine squared is always at least 0. At least 0 plus 1 is at least 0, so this denominator is continuous and never 0. And the numerator, let's see, x to the 4th is continuous, plus 1, this is a polynomial, so what's in the root is a polynomial. It's also always greater than 1, so the square root always exists, so this is continuous everywhere, and so the quotient of those two continuous functions, since the denominator is never 0, this is continuous everywhere. This is continuous as long as 3x minus 1 is greater than 0. That would mean that 3x has to be greater than 1, so x has to be greater than 1/3. So we're guaranteed this is continuous as long as x is greater than 1/3. So it's also continuous in the sense that it has a left endpoint here at 1/3. So the function looks like this. It is continuous, at least from the right. And so as you take the limit as x goes down to 1/3, you have a continuous function. So when we talked about being continuous at an endpoint, that's true. So I guess we'd say it's continuous so long as x is greater than or equal to 1/3, or it's continuous on the interval from 1/3 out to infinity. Let's see, I think we already did this one, so we found that it was continuous everywhere except for at negative 2 and 5. One last example. Is this function continuous? Well, x cubed minus 8 is a polynomial, x squared minus 4 is a polynomial, so the quotient of continuous functions is continuous so long as the function in the denominator is not 0. If x can't be 2 and x can't be negative 2, then this is definitely continuous at those points. Our only question is, what about continuity at 2? So what we ought to check is the limit as x tends to 2 of x cubed minus 8 over x squared minus 4. So that limit gives us 0 over 0, but we can simplify because our difference of cubes factors to x minus 2 times x squared plus x plus 4 all over x minus 2 times x plus 2. So those cancel, so we find the limit as x tends to 2 would be, we're getting closer and closer to 4 downstairs, and then we have 4 plus 2 plus 4 would be 10, so that would be 5 halves. Oop, no, the limit as x tends to 2 doesn't match the value of the function at 2, because the value of the function at 2 is 3, so it doesn't work. So we're discontinuous at 2. We don't even have a limit as x tends to negative 2, because we saw even though we factor this and we're able to cancel out our problem at 2, we still have a problem at negative 2, because as x tends to negative 2 we have, let's see, negative 4, and then at negative 2 we have 4 plus 4 is 8 minus 2 is 6, so negative 4 times 6 over x minus 2, that makes negative 4. But now these numbers are going to be getting tinier and tinier, and so this is going to, on one side, go to positive infinity, the other side go to negative infinity, because we have tinier and tinier numbers there. So we don't have a limit at negative 2. Doesn't exist as a finite number. So it's not continuous at 2 or negative 2.